Hello, students. My name is Shashank Shekhar, and today is the second day of this chapter that is chemical kinetics. So, in the previous class, we have started the chapter lecture chemical kinetics, and today is the second part. So, if you look at the syllabus here, so we had our CBSE syllabus, which says that we have a rate of equation reaction. So, we have covered up till this. Before going to the next topic, we will give a revision to this rate of reaction, as this is important for the chapter. We'll see the application of this rate of reaction throughout the chapter. So we'll give a quick revision to it. After that, we will see what are the factors that affect the rate of reaction, the concentration, temperature, and catalyst. I want to mention here one thing is that today I will just give an introduction of how this, say, concentration and temperature and catalyst affect the rate of reaction. You can say we will do a qualitative analysis, not a quantitative analysis. We will not say that how much it is affecting the rate of reaction. I will just say how, in which way it is affecting the rate of reaction. So today we will be discussing this part on, right? So let us start our today's class. So these are the topics that we will be covering today. So we will give a revision, what is rate of reaction, and we will again see the same examples so that you can remember the concept behind it. After that, we will see what are the factors that affect the rate of reaction. Likewise, the nature of a rate of reaction. So this one is quite a complicated thing to discuss. I would say I will just want to make a statement in this nature of reaction. So the statement that I would try to make is that the effect or the factor that are affecting the rate of reaction are in a some way cannot be quantified or generalized. You cannot generalize them. So that would mainly depend on the nature of the reaction. So we will see what it is. After that, we will see what is the effect of concentration, temperature, and catalyst. So these are the three that is given the syllabus. So we will today only give a qualitative analysis of that, not a quantitative one. We will not discuss the, will not give the measure. I mean, to what extent that change is affecting the rate of reaction. Is this clear? Okay. Now let us first revise the previous thing, that is the rate of reaction. So we have seen that if we have a hypothetical reaction, say we are going from R to P, and we have assumed that the volume remains constant. So why we have assumed this volume remains constant? If the volume changes, the concentration would change in a different way rather than the reaction way. Means I want to say that now the concentration we have to study should only be the change that is due to the proceed of reaction, or you can say the uh, increase in chemical coordinate of reaction. So if we change the volume, this will affect the concentration, that will be not due to our reaction but due to our external effect. Okay, so what we are doing is we are keeping the volume of the system constant. Now we will assume that the 1 mole of reactant R produces 1 of the product P. This should be clear. So we are considering here 1 mole of each of this. Nothing is written before this reactant and product, so it will be assumed as 1 mole. So this equation or this stoichiometric equation says us that we are reacting 1 mole of the reactant and we are getting 1 mole of the product. So it is a kind of 1 molar reaction. Now we are considering that if R1 is the concentration initially and P1 is the concentration at time T1. So we are what we are doing right now is we are taking two concentration at two different times, that is at T1 and T2. Now suppose the reactant concentration at time T1 is R1 and the product concentration at time T1 is P1. So at time T1 we have the reactant concentration R1 and at time T1 we have the product concentration P1. One more thing here, I will assume that this T2 is greater than T1. Now as the time proceeds and T1 moves to T2, so since T1 is less than T2, we cannot move from backward direction. We cannot move toward the backward direction. It is not possible. You know it very well. Time cannot be reversed. So what we are doing, we are moving from T1 to T2, and T2 should be greater than T1 because we cannot move in backward direction. Is this clear? Right. Now, again, we are saying that T2, at time T2, we have the reactant concentration as R2 and product concentration at T2. Now, one thing to notice here is that what are these square brackets representing? So you can see we have square brackets for each of these. So these square brackets mainly represent the concentration. So we are mainly focused about the concentration because if you have remembered the previous class, if you remember the previous class, you must have seen that if you are dealing with liquids, then we will take this concentration, and if we are dealing with gas, then it would be more appropriate to deal with their pressure term, right? So here we are going along with the normal one, that is the concentration. I am saying it the normal one because in the throughout the chapter you will see that concentration term is used mostly. So we are mainly taking this, say, our liquid solution, right? So this square bracket mainly represent the concentration. You will see various square brackets like A, B, like so. Suppose we have a molecule NH3, its concentration will be represented like this. We have H2 gas, its concentration will be represented like this. Suppose say we have our HCl, then in that case also the concentration will be represented like this. So I mean here that the square bracket will always represent concentration. Now let us consider the change what has happened as we have moved from time t1 to time t2. So first of all, what is the time that has changed? So we have moved from time t1 to t2, and we have said earlier that t2 is greater than t1. So what is the change in time? Accordingly, we can write t2 minus t1. Is this clear? Okay. So I am saying that delta t is equals to t2 minus t1. That is the change in time that has happened. Next, what is the change in concentration of reactant? It is R2 minus R1. R2 minus R1. So the concentration has changed from R1 to R2. So the this concentration can be written as change in concentration can be written as R2 minus R1. Similarly, for product concentration change, we can write it as P2 minus P1, where P2 was the concentration at time T2 and P1 was the concentration at time T1. So the change in product concentration would be equals to P2 minus P1, square brackets and all. Now, if I want to define the rate of disappearance of R, rate of disappearance of R, okay, so it would be given by decrease in concentration of R by time taken. So what was the decrease? We have seen it here. It was delta R, R2 minus R1. That would be delta R. And the time change that, or the time that was taken to see this concentration change. So it is represented by delta T. So it is also mentioned here also, which is delta T2, T delta T is equals to T2 minus T1. Therefore, the formula becomes change in concentration of reactant by time taken. But you can see one more thing here. So this is a negative sign. So this is along with a negative sign. So why is it so? I mentioned in the previous class also that rate is a kind of velocity, and velocity can never be negative. Is this clear? So I am saying that rate of reaction is kind of a velocity, and in physics you have seen that it can never be negative. Similarly, the rate of anything, or the rate of reaction, or the rate of disappearance, anything can never be negative. So what do? We take a negative sign along with it. Again, if we want to do it in terms of product, we can write it as rate of appearance of product, or product P, can be given by increase in concentration of product P, because since we are proceeding the reaction in the further direction or in the forward direction, then the concentration of reactant will decrease and the concentration of product will increase. So we can write that the increase in concentration of P can be written as delta P, that is P2 minus P1. Here it is written, and time taken, that is T2 minus T1 again. So in the same time instance, we have gone from reactant R1 to R2, and the same time instance T1 to T2, we have moved from product concentration P2 to P1 to P2. Right. Uh, if you see here, then you can see that we have a positive sign against this equation. Why is it so? I've told you earlier that the product concentration is increasing. And one more thing, that the rate of reaction should be positive. So if we are uh, seeing the change, then it would be positive, obviously, because the product concentration has increased. So final minus initial would give you a positive unit. So we do not need to put a negative sign against it, so that the rate of reaction can be counterbalanced, or the negative can be counterbalanced. So we do not need a negative sign against it. So you should remember this always, that while we write this rate of reaction in terms of concentration, or the rate of disappearance of R in terms of concentration, put a negative sign. And if we are writing the rate of disappearance of P in terms of product, put a positive sign. So the same thing is written here also, that delta R is a negative quantity. Why? Because the concentration of reactant decreasing. So it is multiplied by minus 1 to keep the rate of reaction a positive quantity. So you should just keep this in mind always. Never ever forget to put this sign against your say change in concentration of reactant if we are calculating the rate of reaction. Then we have also seen in the previous class, or this thing, that is an example. So I have put here an example. So this is a quite good example right now, because we have not introduced this stoichiometric term. In the previous class, I have introduced, but right now in the revision part, I have not introduced. So we are taking an equation that is balanced. First of all, it should be balanced. It is balanced, and we do not have any stoichiometric coefficient, or we do not have to multiply by any stoichiometric coefficient to make this thing equal. Is this clear? So we have this reaction in which the Hg liquid is going to HgCl2 by reaction with chlorine gas. So all the stoichiometric coefficient, or you can say reactant and product, are same. Now, if you want to write the rate of reaction, so till now we have seen the rate of disappearance of reaction. Now we'll see what is the rate of reaction. So if we have no coefficient against any of this reactant, we can simply write in terms of rate of appearance and rate of disappearance. So you can write one more statement here, that if the coefficient, stoichiometric coefficient of the reactant and product are same, then, or you can most effectively say unity, then what we can write? We can write that rate of reaction will be equals to rate of disappearance of reactant is equals to rate of appearance of product. So for a reaction whose stoichiometric coefficients are all 1, we can write that rate of reaction is equals to rate of disappearance of reactant is equals to rate of appearance of product. So the same thing is written here. So what we have written is that the change in concentration of mercury by the time that it has taken to transverse that change, along with a negative sign, because we are dealing with reactant, is equals to the negative sign again, because we are dealing again with the reactant, that is chlorine. Its change in concentration and the time taken to make that concentration change is equals to the change in concentration of product by the time taken. And we have put a positive sign because we are dealing with this product. So this was the thing with the same stoichiometric coefficient. Now, if we take a case in which we have different stoichiometric coefficient, so we have taken it earlier also, so I'm just giving it a revision to you. This would be this balance, right? Now, if you want to write this rate of reaction, then we will write it as rate of reaction is equals to, first of all, in terms of N2, if you want to write, then negative delta change in concentration of N2 divided by change in concentration of T is equals to minus 1 by 3 delta H2 by delta T. So you should notice here that I have introduced a 1 by 3 factor here. 1 by 3 factor here. And that factor is the reciprocal of the coefficient that was against this H2. So this is the thing that you should remember. So what you have to do, if in case of the coefficient is not the same, or you cannot say it is not unity, then we have to multiply that rate of appearance or disappearance of that reactant whose stoichiometric coefficient is not 1 by the stoichiometric coefficient, and sorry, by the reciprocal of their stoichiometric coefficient. So this thing I have done for like this delta H2. Now what would be the this ammonia say? So since we have a 2 coefficient against this NH3, so what we will do, we will just again take a reciprocal of that 2, that would be 1 by 2, and since we are dealing with product, we will have a positive sign, change in concentration of NH3 divided by delta T. So this is our equation for this ammonia formation. Is this clear? So this thing should be remembered that if we have a stoichiometric coefficient that is not equals to 1, and if we are writing the rate of reaction, then what we will do is that we will multiply the rate of appearance or disappearance by the stoichiometric coefficient reciprocal. Now, if I want to make further statement in this, suppose you have to find the rate of disappearance of this delta H2 by delta T, and you are given the rate of appearance of the delta NH3 by delta T. Right. So what it is given, that we have to find a rate of disappearance of this hydrogen gas, and you are given that the rate of appearance of NH3 is, suppose it is given as 8 mole per liter per second. So if you remember, it was the unit of the rate of reaction. So how you will just find it? We'll just balance. We'll say you'll just equate both of these. So this will be equated as minus 1 by 3 delta NH3 delta H2, sorry, by delta T is equals to 1 by T plus delta NH3 by delta T. Now we can write this as this thing. So you were looking for this part only. So this would be 3 by 2. What is the value of this? I have given you. It is 8 mole per liter per second. So our answer would be 4 3 are 12. So this would be our rate of disappearance of this H2. Now again you are asked that what is the rate of reaction? So what would be the rate of reaction? Now, if you just take this part and equate it with this one or this one, since you have both of these values, then you can get a rate of reaction. So, first of all, let us see what happens if we take this one. So, we are given the value of this delta H minus delta H by T as 12 mole per liter per second. So, that would give us 12 mole per liter per second. Now, if I want to find it in terms of ammonia, then it would be 1 by 2 is given 8 mole per liter per second. Just find out about this, it will give you the same value. So, you can find it very amazing, and you can see that it is a very good illustration of how you can play with this rate of reaction if you're given the values and all. And if you know the simple basic rule that if just multiply the stoichiometric coefficient with the change of appearance or disappearance and the reciprocal of this stoichiometric coefficient. And one more thing, first of all, always look at the reaction and see that whether it is balanced or not. So this is a balanced one, balanced chemical equation. So it should be a balanced chemical equation. Then and then only you can do this whole of this calculation. So is this clear to all of you? So this was taught in the previous class. Now we will move to today's class topic, that is factors affecting the rate of. So there are four factors which affect the rate of reaction, which we would study in this lectures, upcoming lectures. There are many factors again. We have this phase and all, but for now, we'll keep our discussion limited to this of this four of this topics. I would specially say that we will discuss these three primarily. This one I have put by myself because many of the students try to generalize all of this effect. I want to say to this topic that we cannot generalize it. So let us see how we cannot generalize this thing. So what is the nature of reaction? How what I am trying to give you through this nature of reaction. So the rate of reaction highly depends upon the nature and type of the reaction. I had mentioned earlier, few reactions are naturally faster. So you say that temperature is the only deciding factor or the concentration or anything. So if you keep all these things same for two different reactions, that would not mean that both of the reaction would go at the same speed, because the rate of reaction is specific to that reaction, because different bonds are broken and different bonds have different bond enthalpies that would require different energy and different time, right? So you cannot just say that okay, we have, since we have bond, put a boundary on this parameters like our temperature, pressure, catalyst and all, so we would get the same rate of reaction. So that should not be the confusion, right? So each of these factors are dependent upon the nature of the reaction, the nature of the bonds that are to be broken and that are to be formed. So this was the first thing. Second, the physical state also. So th- it's kind of, you can say, a very complex thing. The second one, which is the number of reactant and the complexity of reaction, other factors highly influence the reaction as well. So the physical state also affect the rate of reaction. Again, the number of reactants also. So I'm just giving a glimpse of you that what is coming in the collision theory, because since it is mentioned the number of reactant, so you must have seen that, or you must have observed what is kind of general thing also, that when we have to carry out a reaction, this reactants and products do collide, and then they form the product. Now, if I have to do the collision of say two molecules to give the product, then the probability would be more than if I have to three other molecules to give a reactant to give the product. So what I mean here basically is that, suppose two reactants are colliding for a given reaction. Two reactants are colliding to give a product. And for a different reaction, three molecule of reactant have to collide to give the product. So the probability of two molecules colliding at the same time is more. You may just imagine it. So they are moving randomly. If three had to collide, then the probability would be decreased. And this reduced, you can say, probability would decrease the rate of reaction. So you can see that how this number of reactant can also define the rate of reaction. Now, the rate of reaction in liquid is less as compared to gases. Why is it so? So I've just mentioned a glimpse of this collision theory that molecules do react upon collision. Now we know very well that gases are moving more rapidly than the liquid one. So since they're moving more, so there is a chance of greater number of collision in a given time as compared to liquids because they're moving randomly. Suppose you put uh, four balls in a room, right? Or say you're taking a carom board. So take a different example. You have a carom board, and in that carom board you have your this whites and blacks. We have white and black type of this say chips. Now they are put upon the carom board. Now suppose we have 10 such chips on the board, and you trigger your say striker. You trigger your striker, and in another instance, what we are doing, we are taking five such chips, and we are triggering our striker. So the case, or you can say, so the probability of striking would be more if the number of this say kind of chips is more. So just make an analogy to it, or you can take a different example also. So suppose this thing gases are just moving very fast. You know very well that the gases have the maximum kinetic energy, or you can say more specifically that gas molecule have the maximum kinetic energy than this liquids and solids generally. Now since they are moving fast, they would not be suppose we have to cover v1 distance to collide, okay, or x distance to collide. So the gases molecule will take less time to collide than the liquid molecules. Similarly, the solid molecule will take more time to collide than the liquid molecule. Now, since the collision number of collision per unit time would be decreased as a result of it, therefore the reaction would go slower. So that is the reason we see generally that gases react more primarily and more fastly. I'm naming it number one, then the liquids, and then the solids. So it is kinds of order. So you can see very clearly that how the physical state of the reactants are affecting the rate of reaction. Next, the size. The size of the reactant also matters a lot. The smaller the size of the reactant, the faster is the reaction. Okay. So the smaller the size of the reactant, the faster is the reaction. Why is it so? The answer again comes from your collision part. Since the smaller molecule will require less thermal energy as its mass is less, so it will require less thermal energy to move around a given system. So the probability of colliding with another molecule will increase. So did you get my point? So we know that kinetic energy of that molecule, or you can say the movement of that molecule, is mainly dependent upon its mass. And if the thermal energy is the same for two molecules, first one is heavier, second one is lighter, then the lighter molecule will move faster, and the probability of its collision, will be more. Now you will say, sir, we have a bigger reactant, so it will cover more area. So the collision of reaction should be also increased. But let me tell you that this size is not that much. Means I want to mean it here that the size difference between molecules is not that much that it would affect the rate of reaction due to their covered area, increased coverage. So it's the speed, the collision, the number of collision that is deciding at last. Now, if reactant molecule exists in different phases, as in heterogeneous mixture, the rate of reaction will be limited by the surface area of the phases that are in contact. For example, so what is meant by here? So it is saying that if we have a heterogeneous reaction, suppose we are reacting two things, one is in solid and one it is is in gas, then the reactants are mixed. Only the molecules present on the surface of the metal are able to collide with the gas molecule. So we know that for reaction, this collision is important. Now, if the both of these reactants are in the same phase, then all of the molecule of the reactant will have a probability to interact with all of the molecule of the other reactant. But if you are taking two different phases, then there would be a phase boundary. Suppose we have a solid metal reactant and a gas reactant. So there would be a phase boundary. So only the molecules that are present at the surface of the solid would be allowed to interact. So that would decrease the number of collision between the solids and gases molecules or the solids or gases reactant, and the reaction would be slower comparatively. So that is the reason we increase the surface area of the metal by pounding or cutting into many pieces. So if you have studied this catalyst, you must have seen that we generally take this finely divided metal. What is this finely divided metal? So I mean here that if the area of this solid is more, right, means more of the molecules are available at the surface rather than the bulk. You get my point? I mean to say here that suppose we are taking 100 gram of solid and we are taking 1 cube. Now in the next set, what we are doing, we are just taking that same 100 gram of solid, but we are taking say 1,000 cubes of say small sizes, right? So that would be more efficient to react. Why? Because the surface area is increased, and due to increase in the surface area, the available number of reactant molecule that is available to react with this gas molecule has increased. That would result in more collision, and hence the rate of reaction would increase. So this is this thing. What the nature of the reaction. So what we have seen till now about the nature of reaction, that we have various reaction, and various reaction have various rates. Like first of all, the physical state of the reactant, then the size of the reactant, then whether it is heterogeneous or homogeneous, and the surface area of the reactant. So these are some of the reactants nature. It means reactions nature. You have means the different reactions of different nature to react. Like if you want to react, say ammonia and this hydrogen, then they are in the same phase. They both are gases, so they will react quite fast. Now, if you consider the reaction, like we are reacting, say a gas with a solid, then it would be more slower. Why? Because suppose first of all, the gases react more faster, and since one is solid, that has put upon a barrier, and second, we have different phases also. Okay, so this is the thing. Now the next effective thing is concentration. So what is the effect of concentration on this rate of reaction? So here I have put up a graph. So this graph is very important. So if you see here, you can see that as this reagent concentration is decreasing and the product concentration is increasing, so you can see that the slope of this both this graph is decreasing, and this slope is only deciding the rate of reaction. You have seen that since it is a concentration axis and time axis, so the slope of the whatever this graph we get, the slope of it is the rate of reaction. Now what will happen if this slope decreases? The rate of reaction will decrease. So if we see here, as we proceed in time, or you can say the reaction coordinate increases, the product concentration is decreasing. Due to this reason, the slope. First of all, you should understand what is slope. I mentioned it earlier also. So what is this slope? This slope is basically the steepness. Steepness means how fast the graph is falling or increasing, both the things. So you can see that this graph is very increasing fastly here. Fastly. But after some time, as the product concentration decreases, this sorry increases, this steepness goes away. Kind of try to increase slowly. After some time, it becomes parallel to this time axis. That is, the concentration has become constant. Now, due to this reason, the steepness has decreased, and steepness decrease means this slope, the tangent that is drawn at different slope, different points. The slope has also been reduced. and hence the rate of reaction has decreased. Similarly, if we take a look here, right, then you can see the stiffness is again going, again fading away with time, right? So this reactant concentration is decreasing, due to which the stiffness is going away and we are getting a reduced rate of reaction. So the same thing is written here, that the rate of reaction will decrease with decrease in concentration of reactant. So you can see very clearly that the reaction rate is decreasing as the reactant concentration is decreasing. Here it is reagent, same thing, no problem. The different second point, that the reaction concentration, if it is product concentration, if it is decreasing, so sorry, increasing, then the rate of reaction would also decrease. Here you can see it very clearly. Now we will see a rate law that would govern, or you can say quantify all of these things. We do not know that what change in concentration of product will affect rate of reaction up to which extent. So what I'm saying here, that we have a law called the rate law. It's very important for this reaction. We will see in the later on lectures. But for now, just remember this term. We will see that how this rate law defines the concentration effect on the rate of reaction. So this was our effect of concentration. Now this was about our effect of concentration. Next, we will see what is the effect of temperature. We'll see. I want to say that this temperature change is very significant in this rate of reaction, right? So we'll see something more about this, but just I'm giving you an introduction. What happens after increasing the rate of reaction, or you can say what is the effect of temperature on this rate of reaction. So if we increase the temperature, what happens is that the rate of both forward and backward reaction, both. So I'm saying it for a reversible one. So if we have a reversible reaction and we increase the temperature, then what will happen? The rate of both forward and backward reaction increases with increase in temperature. So this point should be very clear. So students often get confused that since we are increasing the temperature, so that would result in an increased rate. Yeah, that would result in an increased rate, but both for forward and backward. So if a case happens that the backward reaction is more enhanced, then that would result in the reaction going slower due to increase in temperature. So we'll see it how. So now it depends that which rate is more enhanced by the temperature. Okay, so this should be the point, that we have to now see that which of this rate, rather forward or backward, which of this is more affected by our increased temperature. So if the rate of forward reaction is more enhanced by the temperature, means after increasing the temperature, the rate of forward reaction is more increased, then I would say that okay, the reaction would go faster. Now, if the backward reaction is more enhanced or more increased, then that would result in the decrease in the rate of reaction. Okay, you to get my point. So I want to say that if the rate of forward reaction is more increased than the backward reaction due to increase in temperature, then the rate of reaction will increase. And if the rate of backward reaction is more increased than the forward reaction, then the rate of reaction would decrease. Now, this will be more quantized with the help of Arrhenius equation. So, the first thing you have seen quantization was rate law. That was quantizing our, say, concentration effect. Now, this Arrhenius equation will quantize our temperature. Next thing is catalyst. So, student, I want to make one thing clear here, that student get confused that some things some about like some catalysts decrease the rate of reaction. So they would say, I would not say catalyst also, some substance decrease the rate of reaction. So you cannot consider it as catalyst. So catalyst word means increasing the rate of reaction. So it should be clear. So catalyst, when we are saying catalyst, it means it will always increase the rate of reaction. There is nothing like positive catalyst or negative catalyst. It is a wrong terminology. So catalyst word means itself, it means that it is some substance that is taking sorry, it is increasing the rate of reaction and its concentration is not increasing or decreasing, right? We have a different terminology for the substance that decrease the rate of reaction, that is termed as poison. Okay, so it is not something, a catalyst is not something that would decrease the rate of reaction, and it is the wrong terminology for the substance that is decreasing the rate of reaction. So I have written the same thing here, that what is a catalyst? A catalyst is a substance which speeds up a reaction but is chemically changed at its end. So what do you mean that it is not chemically it is chemically unchanged, or you can say it is not changed chemically, right? At the end of the reaction. When the reaction has finished, the mass of catalyst is same as that of beginning. Is this clear? It is very clear. Right. But one more thing. So some definitions are like this, that it does not take part in a reaction. So this definition is wrong. Catalysts do take part in the reaction. Okay. Without taking part, it would not be possible to increase the rate of reaction. So a more appropriate definition would be that its concentration or its mass or its chemical properties do not change at the end of the reaction, but it take part in the rate of reaction. So you will see in the organic, and you must have seen also acid catalyzed reaction. So that H plus that we have, that protonates the reactant. So it is kind of taking part in the reaction, but at last it is given out, that same concentration is given out. Due to this, it is acting kind of catalyst. Okay, so this should be clear from the very start, that this catalyst is a kind of participating in the reaction. And the second thing, that catalyst always increases the rate of reaction. A poison is something that decreases the rate of reaction. So this 2 points should be very clear in your mind. Now we have several example of catalyzed reaction. So we have the decomposition of hydrogen peroxide. So it happens in the presence of concentrated sulfuric acid. So this is the catalyst that is taken. Again, nitration of benzene is catalyzed by iron. Manufacture of ammonia is again catalyzed or solid catalyst, that is vanadium oxide. Then conversion of SO2 to SO3 is also done on nickel surface. And hydrogenation of this C double C bond is done on platinum. Sorry, it is not written here. Platinum. So you can see one thing here. So this is just above the topic, above your chapter, that if we are taking something that is gaseous or liquid also, then we are doing it on the surface of this solid, because providing a surface area, more surface area to react would result in the rate of reaction, increase rate of reaction. So we will connect it with this surface chemistry. I think it is not in the syllabus also, but you can see here that absorption of this all this gas and liquids on the surface of solid is increasing the rate of reaction. Okay. Now there is nothing here to quantify it, but we will see the Maxwell-Boltzmann equation, and we will see how this catalyst is increasing the rate of reaction. So we'll discuss about it more. So all of these factors I have studied till now, we have studied till now, that is effect of concentration, temperature, catalyst. I've just given a brief introduction of all of this. Now we will just see how does this catalyst does so, what it is doing internally inside the reaction. So if I want to quantize it, the effect of concentration, then we have this rate law. If you have to quantize this temperature, then we have this Arrhenius equation. And for catalyst, we will see Maxwell-Boltzmann. This Maxwell-Boltzmann is also applicable to this temperature. I would say that it is the this RNS equation is a result of this Maxwell-Boltzmann equation, or most Maxwell-Boltzmann distribution, right? So this was our effect of catalyst. So with this, I end my lecture here. So today I will be starting with the effect of concentration again. I would discuss about in more detail. So we'll see what is rate law and all. So thank you for today's time.